So hello and welcome back to the good stuff we have been doing. In the previous video we already discussed how you could express sine x and then cosine of x, and also the hyperbolic sine and cosine in terms of infinite product, but we don't really care about this infinite product, to be sincere, because our main focus is on the series aspect. Not that they are not beautiful or pretty or important, but they are really beautiful. But our main focus on the Mittag-Leffler expansion in series, because it is more useful for the evaluation of definite integral if you have a series than if you have an infinite product. For example, let's say I already discussed that if we have to even find the integral from 0 to infinity of, let's say, sine of x over x dx, we better off using the series for sine. We cannot just say this is equal to the integral from 0 to infinity of x times the infinite product as n runs from 1 to infinity of say x 1 minus x squared over n squared pi squared and then over x dx. The problem is that we don't know how we are going to even integrate such products to begin with, so that is why they're not so useful. But if you have a series, at least you can switch integration and summation, and maybe something good can happen. So that is why we usually don't deal with that. So let's write down our results we already obtained. So we already obtained that, first of all, sine of x, sine of x is equals to x times the product as n runs from 1 to infinity times 1 minus x squared pi squared n squared, and then also cosine of x, we already obtained this to be equals to the product as n runs from 1 to infinity of 1 minus x squared, then you have a 2n minus 1 squared, then you have a pi squared. So these two results, we will try to obtain a series for tangent tan x and then also cotangent of x, because if you recognize that tan of x per se is going to be derivative with respect to s, there is negative times derivative with respect to s of the logarithm of what? Cosine of x dx. Because you take derivative of logarithm of cosine of x, you obtain on the bottom part cosine, and at the top negative sign, and the negative here makes everything to be a plus sign. So in this aspect, that means tan of x would be negative times the derivative of the logarithm of what? The whole of this infinite product, which is the product as n runs from 1 to infinity of what? 1 minus x squared, then you have a 2n minus 1 squared, then you have a pi squared over there. So good things can happen. Next, how do we take derivative? Well, the logarithm of a product is the sum of those logarithms. Then this, for that reason, so you are taking this is going to equal negative times the derivative with respect to x of what? The sum as n runs from 1 to infinity of the logarithm of what? 1 minus x squared divided by 2n minus 1 squared, then pi squared. Now if you take derivative, you will have negative times the sum as n runs from 1 to infinity of, at the bottom part, you have a 1 minus x squared divided by 2n minus 1 squared pi squared. Then at the top, you will have a, I forgot that it's going to always be a 4 here. There's always going to be a 4 here, and there's always going to be a 4 here. So at the very top, you have a negative 8x divided by what? 2n minus 1 square, and then you have a pi square. So the negatives cancel out. So you obtain the sum as n runs from 1 up until infinity of, at this part here, the bottom part would come down. So you would have 8x to 8x, then you would have 2n minus 1 square pi squared minus, so this is going to be a 4, minus 4x squared. So that is the series for tangent of x. So it is clear by now. So we recognize that tan of x is the sum as n runs from 1 to infinity of 8x, all divided by, on this side you have a 2n minus 1 squared pi squared minus 4x squared. So this form is extremely useful for series. And if you notice that you can also find the series for hyperbolic tan of x, because that would be tan of x, I think that would be negative I times tan of ix. So if you plug that, you should obtain, okay, let's go to a fresh new page. So we already established that tan of x is equals to the sum as n runs from 1 to infinity of 8x divided by 2n minus 1 squared pi squared then minus 4x squared. So like as we say, you have the hyperbolic tan of x will be negative I times the tan of ix, right? So which will be negative I times the sum as n runs from 1 to infinity. So ix here would be a negative because I'm not even sure for this relation. Let me see. Tan of x is sine of x over cos of x, which is negative I sine of ix, all divided by cosine of ix. So yes, that's correct. So you have a negative I times that. So you have a negative 8ix all divided by 2n minus 1 squared pi squared. Then you have a plus 4x squared. So that would be the sum as n runs from 1 upon to infinity of 8x all divided by 2n minus 1 squared pi squared plus 4x squared. Yeah, so I think that one is in the back. Now what remains for us is to do the same for cotangents, okay? And let's take this out. For cotangent, I don't think we're going to suffer too much, because it is clear that cotangent of x, okay, let me see. It is clear that cotangent of x per se is going to equal the derivative of the logarithm of cosine of x, right? No, logarithm of tan of x rather. No, logarithm of sine rather. Yeah. So basically, this is going to be the derivative of the logarithm of the x times the product as n runs from 1 to infinity of 1 minus x squared over pi squared n squared. Okay, and that would be the first of all, this would be d dx of first of all log x, and then plus the sum as n runs from 1 to infinity of the logarithm of 1 minus x squared, then you have a pi squared n squared. So let me take out these parts of the board. We won't be needing it. So in this case here now, this will be equals to dds is going to be equals to 1 over x, then you have a plus sign, then you have the sum as n runs from 1 to infinity of what? At the bottom you have a 1 minus x squared pi squared n squared, and at the very top you have a negative 2x divided by you have a negative 2x divided by the bottom part, which is pi squared n squared, and as things goes, this will be 1 over x minus the sum as n runs from 1 to infinity of, at this part you have it twice, so you have the sum of x divided by pi squared n squared, then you have a minus x squared. I hope so. Yes. Yeah, minus x squared. So this is cotangent of x. So you have that cotangent of x is going to equals to 1 over x minus twice the sum as n runs from 1 to infinity of x divided by pi square n square minus x squared. Although the useful way of writing this sum is writing this as twice the sum as n runs from 1 to infinity of x divided by pi squared n squared minus x squared as 1 over x minus cotangent of x. So basically the sum as n runs from 1, let me put this in red color. So essentially the sum as n runs from 1 to infinity of 1 over n squared pi squared minus x squared is going to equal 1 over 2x squared minus cotangent of x divided by x, cotangent of x divided by x. So this is the useful way to write it. And you notice that again, cotangent of x, I think cotangent of x should be the hyperbolic cotangent of x should be still be negative I times cotangent of ix, because you have cotangent of ix to be cosine of ix divided by sine of ix, and you have to multiply by negative I, right? Okay, you have to divide by negative I, negative 1 over I, but that's the same thing. Okay, if you divide by negative I, you have a negative I here, but you can still multiply the top and bottom by I here. So in this part, if you do multiply top and bottom by I, so you have a I, it will be I cosine of ix divided by sine of ix. Okay, so which is going to be I cotangent of ix, and if you multiply by negative I, so you see get cotangent of ix. So you see the same thing. So basically you need to put only ix here, and if you do that, you put ix here and ix here. For this part, if you put ix here, you would have a plus sign, then this side it will be a negative, but for here, cotangent of ix divided by negative I would be I tangent of cotangent of ix. So you would obtain the series for hyperbolic cotangent, which is clear. So that should be that. So we already have the series for sine. We already have the series for. So we already have a series for sine of. We already have a series for tan of x, rather cos of x, not cos, cotangent of x, and also for tan and cotangent of x. So if you want to obtain for 1 over sine of x in the series, what you need to do is that you need to multiply top and bottom by, say, sine of x over 2 divided by sine of x times sine of x over 2. So in this case, you write it as sine of x minus x over 2, all divided by sine of x times sine of x over 2. So you would obtain sine of x cosine of x over 2 minus sine of x over 2 cosine of x, all divided by sine of x sine of x over 2. So in this case, this cancel out. So you have a cosine and sine. So you have a cotangent of x over 2. So here they cancel out, and then you have minus cotangent of x. So you already have the series for cotangent of x. We know that cotangent of x is equals to 1 over x minus twice the sum as n runs from 1 to infinity of x all divided by x squared pi squared x squared pi squared n squared, yeah, pi squared n squared minus x squared. Let's check the previous board. N squared pi squared minus x squared. So yeah. So now what you need to do is that we need to find the series for 1 over tan. So 1 over sine. So rather, so let's go to the next page. So you will know that already we have already established that 1 over sine x is going to be cotangent of x over 2 minus cotangent of x, and it is clear that for us that cotangent of x, let's put it in red, cotangent of x is this is 1 over x minus twice the sum as n runs from 1 up until infinity of what, x divided by pi squared n squared minus x squared. So essentially 1 over sine of x here is equals to the sum is, okay, no, not yet, it's going to equals to 1 over because you, first of all, you have a cotangent of x over 2, so you have an x over 2, so you have a 2 over x minus twice the sum as n runs from 1 to infinity of x over 2 here divided by what, so you have a pi squared n squared minus what, x squared over 4, and we are going to subtract all of these from the sum of from 1 over x minus twice the sum as n runs from 1 to infinity of x divided by pi squared n squared minus x squared. Now you have to worry about 2 over x minus 1 over x, so that is 2 minus 1, that is 1 over x, right? Yeah, so you have 1 over x, so you have a 1 over x here minus, so this will be a plus 2 and this will be a minus 2, so you have the sum, so you have plus the sum as n runs from 1 to infinity of, so you would have the first denominator here, you have the first denominator here, x over pi squared n squared minus x squared, subtracting okay, let me just put it as 2x, subtracting x divided by okay, let's go up, let's say we okay, you have pi squared n squared minus x squared over 4. So now we need to put this in one denominator. So to do that, we could multiply, we will have a 4 here, so you will have a 4 here and then a 4 here, and then you strike out this 4 at the bottom here. You strike out this 4 at the bottom here. Okay. So now all that we need to do now is to collect like terms. So basically all of this is going to multiply this, and all of this is going to multiply this. After we simplify the top, and then we obtain a neater denominator for our sake. So this is what we'll do. This, let me see. So at the very top you have a 2x, then you have a 4 pi, so let's just do the top first, 4 pi squared n squared minus 4 minus 4x, then you have a x pi squared n squared minus x squared. Okay, wait, this will be a x squared. Yeah, x squared. So you have a 2x times this, so you have a 8x pi squared n squared minus 2x times x squared. So you have a 2x to the third power. What about this part here? Then you over here you have a minus 4x pi square n squared, then plus 8x to the third power. Okay, there is even no need for all of this madness, because if you observe, these two series are almost similar, except that in one of them, this one seems more like all the terms containing even multiples, okay, while this one seems to be all the terms. So this one contains only the even multiples, while this contains only all of the terms. So if we do the subtraction, only the odd terms will be remaining. So you would, on the first page, obtain that you will obtain that cotangent 1 over sine of x would be 1 over x times plus the sum as n runs from 1 to infinity of negative 1 to the n. You have a 2x divided by what? X squared minus pi squared n squared. Yeah, so that is that. You can do the same similar thing for 1 over cos, and from there you can obtain 1 over sine x, and then 1 over cos os again by changing x to ix and the rest. So you see that it's a lengthy process, but you would always have a handy table featuring all this. They call them the Mittag-Leffler expansion. So thank you very much for tuning in and watching, and please do subscribe to the channel. Bye, and do have a nice day.